Hey class, Adam Ward here. I wanted to try something today. We'll go ahead and do sort of a derivation related to forces that act on planar surfaces. This is part of our hydrostatics unit. And we're going to go ahead and talk through this on the web rather than in class. So hopefully we can work with these concepts in class and you can have this derivation for your own records as you see fit. So I want to start us off with this definition sketch, which we'll use throughout the lecture today. There's a couple of important points in here. Shown in green on this is the centroid. And so that sort of jelly bean looking shape at the bottom that says frontal view, you can think of that as some arbitrary shape that's submerged below a liquid, or within a fluid, I should say. Green is defining the centroid, so these H's are defining depth from the water surface down, and these Y's are defining distances along the angle of that plane. So we've got an inclined plane at angle theta relative to the liquid surface. Green is showing you the centroid. In blue, you're seeing what's called the center of pressure. That's the location where the resultant force would act. So if you took all of that force and tried to just acting over the shape and tried to resolve it into sort of an equivalent force at a point, that's where that would act. We'll talk a little bit more about that in class and in another video. And in red is an incremental area that we're going to begin by analyzing. So it's at some arbitrary depth h, some arbitrary distance along the wall y, and there's an incremental force df that would act at that location. So there's the same picture. We've just given ourselves a little bit of space here. And so I want to start by calculating the force for our slice of this area. And we know from previous work that we've done together that force is equal to a pressure acting over an area. So force is P times A. And for our incremental area, dA, there's an incremental force dF that's acting on it. Now from there, we learned that in hydrostatics, pressure can be expressed as the specific weight of the fluid, that's gamma, multiplied by the depth. In this case, we're using h to represent the depth below that liquid surface. So we can plug that in and update our equation here. Incremental force is equal to specific weight times depth times that area. I'm going to switch from using h's to y's just for a moment here. And so what I'm doing is just using right triangle geometry. And so I've kind of sketched that in with green in the top right of the screen here. The depth h of our system could also be expressed as the distance along that plane y times the sine of theta. So I'm going to go ahead and just make that quick substitution here. The reason why will become apparent in a couple of steps, so stick with me and have faith. And so all we're doing is using our definition sketch and what we know about pressure and force to sort of update this equation a little bit. So from here, this is the force on an increment of area. And what we're really after is the force acting on the entire surface. And so how do we go from an incremental area to the entire surface? Well, we integrate over the area. And so that's what I've written in there in blue, the integral signs over the area. And when we do that, we can pull the constants out in front of the integration sign. So specific weight of the fluid doesn't change, sine theta doesn't change. And so I'm just rearranging some terms, right? So y does change over the area. That's that distance along the planar surface. And the reason that we've set it up this way, the reason that we switched to working in y's, we'll show you in just a moment. So if we integrate the incremental forces over the area, we get some total force. And this integral on the right-hand side, if you've taken a statics class or if we look into sort of statics in the sense of sort of physical forces and how areas are distributed around axes, that integral is equivalent to what's called the first moment of the area. And basically that's y at the centroid times the total area. And so we can go ahead and make that substitution back in. So our equation looks like this now. So we've gotten rid of our integration. We've integrated this over the entire surface. And again, using right triangle geometry, and I've sketched it in orange up there, you can see that y of the centroid times the sine of theta, well, that's equivalent to the depth at the centroid. And so what we end up with for the total force acting on this plane is the equation I've boxed in here at the bottom. The total force acting on that surface is equal to the specific weight of the fluid times the vertical depth down to the centroid times the area. And this is actually a really useful equation for us because although we had this strange arbitrary shape, the total force is actually not that complicated to calculate. Right? That total force depends on the pressure at the centroid. And we remember from previous lectures that pressure at the centroid could be expressed as something about the fluid properties and the depth, so gamma times hc. And it depends on the total area. And so that's not too bad. Area of something that's generally easy to measure or something we might be given in a problem or in a design. What I think is also interesting to acknowledge here are the things that the force doesn't depend on. So the total force acting on that planar surface does not depend at all on theta. You can take the same shape, whether it's vertical, whether it's tipped, whether it's flat, tipped the other direction. If you're rotating it around the centroid of that shape, the pressure, the forces arising due to hydrostatics don't change. So that force has nothing to do with the orientation of your shape, and it has nothing to do with the shape itself. Right? So if we have 2 square meters, it doesn't matter if it's shaped like a square, a star, a circle, an arbitrary shape. It's just the total area that matters in this case. And so what we'll do this week and in our class is we'll use this as sort of one of our key equations for hydrostatics, being able to relate forces that fluid is imparting on an object to fluid properties and the geometry of the problem. Hopefully this derivation helps. As always, you're not expected to be able to do the derivations on your own, but I want you to see where these things come from, sort of fundamental physics and how we get to the equations that we'll use in class. And with that, I will sign off for this video. Thanks, everybody.